We had a person who was in the water, realized they needed to get back on land. They were going here. They started here. This was 16. That was 30. We decided to put this person in the coordinate system. This story is all about this person, yet we still didn't put that person at the origin. That's okay. Right? So we made the origin here, the closest place on land. And then the question is, as this person swims, where should they swim to so that they can start running? And of course, we had made the remarks that this certainly depends on how fast this person swims versus how fast this person runs. And so we'll see how that impacts this and may offer some extra credit. We were asking, of course, where should this person land so that they arrive here in the fastest time? Minimize the time. We're trying to minimize the time. Square root. The total time is the time in the water plus the time on land. And of course, we got the time by taking the distance in water divided by the speed plus the distance on land divided by the speed. Of course, the game's over. We're going to take a derivative, set it equal to 0, and solve all of that nice stuff. G prime of x is equal to, well, I think let's go ahead and rewrite first. I'm going to get this in, I'm going to prep this. I feel like a doctor. I'm going to prep this for derivative surgery, right? X squared plus 256 to the 1/2 plus 1/5 times, actually, let's just go the whole way. It's 6 minus 1/5 x. Right? That is t of x, right? So I've rewritten this so that it looks ready to go for derivative, and then we'll take one. I'm going to set this equal to 0 and solve. Equals 1/3 times 1/2 x squared plus 256 to the minus 1/2 times the derivative of x squared plus 256 plus 0 minus 1/5. We're looking for x. X should be some number between 0 and 30. This is equal to 1/6 times 2x times 1 over the square root of x squared plus 256 minus 1/5 is equal to 0. And so that's, yeah, okay, great. This says that x over 3, the square root of x squared plus 256 is equal to 1 over 5. We'll cross multiply and start solving for x. 5x is equal to 3 times x squared plus 256, and we'll square both sides. Looks like we're going to get there. no issues. Square both sides. I should write that in a different color. Square both sides. (25x squared) equals 9 times x squared plus 256. (25x squared) equals, they actually set this up nicely. Plus 9 times 256. Kind of nicely. 16x squared equals 9 times 256. X squared equals 9 times 16. X is equal to plus or minus 12. All algebra there. Given the context of the problem, we of course will take the plus. And we'll say this is not feasible. Well, usually this number looks horrible. But they set it up so nicely. Right? So 12. 12 miles down the road. That's where they should land. You can find the time by plugging in 12 and answering whatever question I have. So again, I'll be looking for something like this. This is like a 10, by the way. This would not be a test question. It's not even close. Right? It just takes too much time. But there's so much other stuff to do, as you'll see on the test. I'll open the floor for questions about this, any of these steps. Right? So again, the point of this was to see, again, one of the applications of optimization, please. Yes, absolutely. Thank you. So one of the applications So bottom line, story, look for what I'm trying to maximize or minimize, create that function, and then derivative stuff. That is the challenge. Are we good? Here? Okay, excellent. All right, so let's talk about material for test 2. This thing's going to be crazy, right? Test 2, material. 1, we'll talk about the definition. Of derivative. And 2 interpretations. I'll open the floor to questions on that. I'll try and keep a straight face. I can't do it. That's number 1. We ended up talking about inverse trig functions, so we need to do that stuff. So that will just be I believe so. I'll make it so that's on the points. Please.
Are we going to have another review the day before the test?
Say it again?
Sorry. Are we going to have another review day before the test?
Yeah, I mean, I'm debating having 2. Yeah, I mean, it's just a lot of stuff, right? So it may be Wednesday and Thursday. Yeah. No one ever does that, right? So I just want to make that clear. No one ever has 2 review days. No one really has review days. Again, the person that I'm tutoring usually get, in at these schools, like at Penn, they just give you this huge review packet, and you just figure it out. And of course, the review packet has all these things, because what professors do is they take advantage of the fact that everyone values the review packet, and that's their chance to put in all this hard shit. Like, everyone thinks it's the review for the test, but it's just our chance to say, okay, you're paying attention to this, do all this hard stuff too. And every fifth problem is actually on the test, right? But then you don't know which ones are on there, right? So I'm way more straightforward than that. But usually, people don't usually take class time to review. So, but yeah, we might review. I want to honor the fact that we are going at a lightning pace, right? I mean, again, you're coming from a context where you would take 2 semesters in high school to do a lot of this stuff, and we're doing it in 5 or 6 weeks. That's crazy, right? So, I do want to review. Okay, inverse trig functions. What else did we do?
Related rates.
We did related rates.
Implicit.
Yeah, so we'll put, that's fine. It doesn't matter the order. So we'll do some related rates, some implicit differentiation, there's some first and second derivative test. I'll see what Jessica is up to. I may have her make a review test in the homework system with all of this stuff. And so this is all increase. So this includes increasing, decreasing, concavity, all of that stuff. So we did a mock test question about that stuff. There was something else in my mind. Optimization. The mean value theorem. Well, let's be clear, right? So I'll ask you to state the mean value theorem. Mean value theorem.
Exactly how you did it in during class.
I'm as straightforward as you can. I mean, I'm not asking anything crazy. There'll be plenty of people you have that are going to be crazy. State the mean value theorem and a geometrical interpretation. Geometrical interpretation. And then there'll be some conceptual problems. And then this is not necessarily the order. We'll get the order clearer as we get closer to the test. Sketching a graph given information about f prime and f double prime. So when we say f prime is positive, f double prime is negative, right? All that stuff. I think that's it. Please.
Is the mean value theorem the only one to write out?
I mean, I don't. So. Oh, it's the only one that I'm going to ask you to write?
Yeah.
Oh, yeah, that's the only one I'm going to ask you to write. Yeah, the mean value theorem is the only one that I'm going to say state this. Yeah. I mean, again, I wouldn't do this and then all of a sudden say state Rolle's theorem. Again, I'm pretty sure for it. So we know how to get ready for a test, right? If you know that this is the material, I've been tutoring for 20-something years. The best students simply, even if a professor doesn't do this for them, they do this for themselves. Get all the material down, go through each one and rate their confidence for each topic. You should do the same. What do you find best? What don't you know the best? I spent a whole hour and a half with Skylar last night talking about one thing, right? And because he had gone, that was the one thing he needed to talk about, right? Because he had made sure that he was ready to do all the other stuff, and he's at Penn. Okay, so you need to do the same thing. Okay, questions about this? Yeah.
Are you gonna roughly use? Because on the homework, it's like.
Oh, yeah, the homework is different. Again, yeah, the programmer for that. Yeah, I mean, yeah, but I mean, if you haven't seen me use one, and then you don't need to use one, right? I mean, again, you can circle 5 square root of 4 plus 3.278, right? Or 7 pi. That's the answer. Other questions about this?
So is this like the final list for the test, or you're gonna like add it at the end of
Say that again.
Is this like the final list for like everything on the test, or you're gonna like?
No, this is it.
Oh.
This is it. Yeah, I'm not adding another thing. This is all. I think it's enough. I mean, these take a while. I mean, I was going to give 2 of these. I mean, this doesn't take that long, but it has like 8 parts, right? I mean, so I'm going to give you a polynomial and say, where's the increasing, decreasing, concavity, where are the critical points, where are the inflection points, use the first derivative test, use the second derivative test, right? So just practice and just be able to just run through that. I'm going to give you some dumb story, and I was thinking about 2, right, where you're going to have to find the greatest this, find the closest that, find the largest this, right? One of these will be hard. That's trivial. So, I mean, this is a vacation, and then you're going to have to think here. I mean, so we're going the whole way, the whole 90 minutes. You're going to need the whole 90 minutes. So you just have to be ready to do it. Right? And this is why I'm talking about it the week before, because I want us to get ready for it. I want Jessica to get started. But what I want you to understand again is that, as you move farther, less and less people will be there to help you, and you have to start doing these things for yourself, right? So, please.
Could you summarize the extra credit as well?
Now, I have no idea what I asked you. But we can, let's see what the extra credit is. That's good too. So then the extra credit, that's why I have you all. What do we say for the extra credit?
Was it the one where like if f of a?
So there's something about the mean value theorem, right? So show why. So the real question is show why differentiability is necessary for the mean value theorem. So that's really what I was wondering. Why do you need it to be differentiable? And so the way that I had phrased it was draw a continuous function where f of a was equal to f of b, yet f prime of c was never 0 for any c. And then there was some extra points is that if you can actually, so you can draw it whatever you want, but if you can actually give me the function f of x equals y, there were more points for that, right? So the mean value theorem says, look, if you're smooth and you start at here and you end at the same place, then you have to have a horizontal tangent, right? You have to, right? But that's, so why is it that you need it to be smooth? It's because if you're just continuous, it's not true. Right, so can you draw something? And again, we gave a hint yesterday for a function that was very close to that. And then the question is, if you can draw it, can you actually write what the function is analytically? Yeah.
So giving the functions kind of like extra credit to the extra credit.
Say it again?
So giving the functions like extra credit to the extra credit.
It is. I told you I have a problem. Yeah. And then, well, so let's step back. So yeah, I have a problem, but I just want you to think. I just want you to think, right? So, and I already see a bunch of thinkers in here, right? But it's the thinkers that, I mean, all these supposedly successful people are deep, deep thinkers. They think about things. They go deeper, right? And the big point is they think about things that they don't even like, right? Because they know that that's what's required to be successful, right? That they fight through the things that they can't even stand, and they think hard about them, right? Anyway, floor was open. Go ahead.
Do we still have to do the constant for inverse arc sine plus arc
Yeah, that's due this time. Yeah. So then the other one, there are a bunch. But then, we had made a comment about trig functions, inverse trig functions.
How much is that one work?
I thought it was, wait, which one?
The first one.
The first one? How many points did we say here?
You can probably search up like on your computer.
I know, but you all have it, right? You can search too. I have 30 people who could look, or I could find in this big old document. Well, maybe I would beat you. Maybe you're right. Maybe I would beat all of you to find out what the number is. 2 points. This is 2 points?
It goes 10.
Oh, 10? You all just flat out lying to me. Now, see, I can't even trust you. This is crazy. This isn't 2 points.
4.
Oh, because it was just drawing. This was just drawing something. So, okay, so this part was 2, right? Just drawing this. I still don't think that's high enough. I do have a problem. Well, okay, so that's 2. But then what was this?
You didn't give it anything.
So, okay, so yeah, maybe it was an extra.
You just added.
Yeah, let's add another 2 points to that. But we'll just change it. That's fine. Yeah. So if you can actually write what the function is, that's 4 points. And then we had made the claim that arc sine of x plus arc sine of x plus arc cosine of x is a constant for every x. And the question is, what was this constant? We actually, we kind of showed this. Yeah, so we can show this using the mean value theorem. And so what is that constant? That was definitely 2 points. Yeah, because, again, we know what that is. And then other extra credit.
There was
Oh, was it? Oh, yeah, okay, great. So show that the derivative of inverse cos. Are we sure? I don't think that was extra credit. No. Yeah, but I think that one was kind of easy, right? Because no, that was not extra credit. Yeah, I'll debate that one. That one's flipping in my mind all of a sudden. No, go ahead.
There's another extra credit of the y equals negative 2x.
Oh, the one yesterday. That's right. So if we had, this is good because I don't really know how to do this one. So you got something at the origin. You got this line coming down like this. Is it always true that the closest point is the one that's perpendicular? Does it have to be perpendicular? Yeah. I don't know the answer to that because it seems like if you make this super close, right? Oh, let me state this formally. So show that. Oh, or I guess this is discuss, right? So is it true that for y equals negative mx plus b, where m is positive and b is positive, that the closest point on that line to the origin is on the perpendicular line? Yeah, is that true? Right. So the point is that I did a problem when m was 4 and b was 3 or something like this, and you just work through the same thing and see if you get that the point that you get is on the line y equals 1 over mx. Yeah. So again, you may need to do a few with numbers again, right? So I mean, mathematicians always look like geniuses, but in the background, we're just doing tons of examples. And then we do all the examples and come in front of you and say, oh, look, notice this. And then everyone says, well, how did you know that? And we're just like, All right, this is one of those things. So yeah, I did one example. Do more and more and more. Because when you do examples, then you see how things work. Why is it that it works? Because of these numbers. And then when you do it with enough numbers, then you'll see how to do it with letters. Okay? Others? And this is worth 8. That's what I thought. Okay.
I think this is not, so if f prime is less than 0, then f is decreasing.
That was on the first time.
No, it's like opposite.
You switched it.
It's the opposite way. You told me you should.
Oh, the other way. Oh, okay. That what? That if
If f prime of x is non-negative, is negative, then f
Oh,
is
okay.
increasing.
Okay. We did do the other way.
You said we
It's
could
called
do it
the.
one way, but not the other way.
It's called the converse. It's called the converse. That's right.
I was 4 points.
Okay, thank you. Good. That shit. Okay. Questions about the extra credit? What is that? That's 12.
There was another one.
Go ahead. What is it?
The claim is that if h of x is increasing, then the critical numbers for g of x
I love it.
h of f of x are the critical numbers for f.
And what was the function inside?
No,
F?
it's none. It's just h of, yeah.
If F, right. If F is increasing.
No, h of x is increasing.
So H was inside? No, H is increasing. That's right. If H of X is increasing.
And the critical numbers where g of x equals h of f of x.
Numbers for H of X equal to G of, I'm sorry, G equal to H, right?
Yeah.
G of X equal to H of F of X. Are the same.
As the critical numbers of f of x. 4.
Right, and so this derived out of the fact that we could drive the square root. Right? Excellent. And how this was worth 5. Oh my God. So many points. So many points. 9, 17, 19, 23. That may be a record. All right, so yeah, no excuses. No excuses. Up. I'm at the bottom right. Okay, that's it. These points add anywhere. So you can go back and add these to the first test. They add anywhere. Redemption. I'll open the floor to questions about anything about the test. All right, we're about to move on. So we were talking about the derivative. It's half of Calc 1. We're going to talk about, it's half of calculus. We're going to talk about the other half of calculus, integration now. The derivative measures the rate of change. It's the instantaneous rate of change, slope of the line, tangent to the curve. I hope you saw some of the applications whenever you're talking about maximizing or minimizing. The derivative comes up in the sense when things are nice and smooth. So there are some times where the derivative does not apply when you want to find the maximum and minimum values of things, right? So we can talk about that at some other point. All right. Integration. It's chapter 3. When I had talked about the derivative, I talked about the problem we were trying to solve. How fast are you moving at this moment, right? How fast are you moving at this moment? And so now I want to phrase the new problem that we're trying to solve, and it's in this case, it's initially the area under the curve, but in a lot of ways, it's trying to find the total amount of something. So we'll take our friend y equals x squared again. And let's say on the interval 0 to 3, So the question is, what is that area? So you're going to have some function, and you can see probably why we want to answer this question. F is going to be some function, and so the area under F is going to represent tons of different things. The total amount of this, total revenue, total distance, total, okay? We see this already in statistics where, again, the normal curve, right? Finding the area under this gives us what? Probabilities, for sure, right? So that in the back of that statistics book, all that stuff is just the area under the curve of this particular graph in certain places. Right? So yeah, we'll have so that one was was proportional to e to the minus x squared, right? And with the translation, it was translated to the origin. It was already at the origin, but then there's a constant in front, so that the area under the curve over the whole real line is 1. Right? And so we need to talk about that. We won't actually talk about finding the area under the curve over the whole real line of something. Right? That's a very interesting question. But let's just start here. How do you find this finite area? So what are we going to do? This is not trivial, but at least we do know the area of certain things. I know the area of this box at least, right? I know the area of this. So a very crude estimate, a terrible estimate of this. What is this number right here? It's 9, right? If that's 3, this is x squared, then 3 squared is 9. I know the number is less than 27. Right? Okay. So that's about the worst I've ever approximated an area with a rectangle in my life. Right? So the area is less than 27, right? Because this whole area is 27, right? We want to do a little bit better than that, obviously. Okay. So what we're going to do is we're going to approximate this area. So I'm going to take the same function. So 0 to 3, not drawing the scale. And then we'll get Desmos to do some work for us after we do a little bit of work ourselves. So we know the area of rectangles, so we're going to use rectangles to do this. So we're going to break the interval 0 to 3 into pieces. 1, 2, 3, 4, 5. Let me add one more. 6. I'm going to break the interval 0 to 3 into 6 pieces. Now, I want to be clear about something, that this is the way that I'm going to approximate, right? That there was this function given. It was given over an interval, and I've been tasked to find an approximation to the area under it. Okay. And so then, I'm going to do it the way I want to do it, and then we're going to talk about some uniform ways that everybody approximates, right? So numerical analysts do this all the time. There are methods to approximate certain things, right? So I'm going to do my funky way, and then I'm going to say, this is how a lot of people do it. This is called this method. Other people, you can approximate this however you want, right? But there's going to be a uniform way to approximate the area under this function and other functions as well. Right? At some point, we'll get tired of approximating, and we'll want to know the exact answer. And as we try and figure out what the exact answer is, there's going to be something that makes a return that we're going to use to get the exact answer. And then we'll realize that the whole class was about this very thing, whatever that thing that comes up. And then, sometime next week or 2 weeks from now, we'll see why in the world we would make this ridiculous jump from rates of change to area under the curve at this point. It makes no sense to talk about both of these things in the same class, right? That it just seems like a ridiculous departure to talk about one and then switch to the other one. And then we'll talk about why that is, right? I have to make sense of why we're making this switch. Okay, so, and then now, what I want to do is I want to create rectangles, right? So I'm going to use this rectangle here, this one, like this. I'm going to approximate the area under the curve using these rectangles. The Great Skeptic has come in. It's been a while. People are starting groaning when the Great Skeptic comes in. He says, look, you want to approximate using these rectangles, you're going to need to give me the length and the width of these rectangles. I said, okay, that's fine. And so I'm doing this however I want. And so I have all of these rectangles, and it looks like I'm going to make them all the same width because I can. Right? Now, sometimes it may be nicer. This picture is certainly not drawn to scale. Early on, it looks like that this is, the derivative here is very, very small near 0. The derivative is 2x, and near 0, 2x is close to 0. So maybe I want to choose a rectangle that's different from a rectangle here, right? And that's very possible, right? But I want my rectangles to all be the same length, okay? The same width, I'm sorry, the same width. So the same width. If that's true and I picked 6, what's the width of each one? Is that okay? 0.5, right? So the width of each one is the length of the whole interval, 3 minus 0, divided by the number of rectangles. What's also nice is that when I make them the same width, then I automatically know all of these points. What's this one? It's 1/2 because the width is 1/2. 1, 1.5, 2, 2.5. The Great Skeptic will come back and we'll have a serious indictment about what I'm about to do for sure. Questions on that? So now, but she is left because now I have the height. I have the width. Do I have the height? How do I know the heights? Well, I have the function. The function is x squared. The function is x squared. So now I have all the heights, and now I can do some approximation. Let's get one. So an approximation to the area is the height is the area of this rectangle. That would be, what's the width? 1/2. What's the height? 1/2 squared. That's right. So it's 1/2 times the height is 1/2 squared. Right, we gotta do this. Let's just do this. Right. Okay. Plus, I need the distance here. It's always going to be 1/2. That's the way we set it up. Times the function at 1. Right, so this here is 1 squared. And then you see the pattern. 1/2 times 3/2 squared plus 1/2 times 2 squared plus 1/2 times 5/2 squared plus 1/2 times 3 squared. We all recognize that this is 1/2. You can pull out a 1/2, but we'll leave it like this for the moment. How can I? Say it again? Oh, it's still eraser. Okay. Yeah. Questions there about that? Now, I chose a lot of things. Oh, let's see what this number is. What is this number roughly? What is this number? 1/2. Say it again? Yeah, what is that? What is that number? See, this is where you may need a calculator, right? Or actually you can leave it like this, but it's purposeful for us to know this. So 0.5 squared plus 1 plus 1.5 squared plus. Say it again? 11.375.
Yeah.
Okay. Is this more or less than the actual answer? More, right? It's clear that the rectangles, calculating the area, that we have this extra stuff. So we say, well, where did I go wrong? Well, it looks like I have this extra stuff. Maybe how did I pick these heights?
Fun.
So I went here, right, in this interval, and I wanted the height to be here, right? And in this interval, I wanted the height to be here. And I did that for all of them, right? And so that's a particular method, and that's called the right endpoint method. That is the right endpoint method, right? So that when you break up the interval into pieces, if I choose, again, I get to pick the rectangles. That means I get to pick the width and I get to pick the height. And so I decided I wanted the width for simplicity to all be the same, but I still get to pick the height. And I chose the height to be at the right endpoint for all of those values. Go ahead.
I don't know if it's called right and stuff.
Right, some people do call it the right
Oh,
endpoint.
so it's the same thing.
Yeah.
What about trapezoids instead of rectangles?
I could use trapezoids instead of rectangles.
Wouldn't that be more accurate?
I think for this one, right, if she said, yo, it's clear that I should approximate this with this thing, she would be dead on right. I mean, they look like trapezoids for sure. And why are trapezoids great for smooth function? Because locally they look like straight lines. Right? So trapezoids crush both methods in a lot of ways, right? Good, good. So when the skeptic comes in, I need to rectify why I prefer this over trapezoids or why it may not matter, right? Okay, good. What's the answer? What is the actual area? What's the actual area? Okay, good. Well, that's what we need to find out. We're going to find out. Now, okay, so what I want to do now is I want to make a following remark that there are two things. The next thing is that, again, I picked the right endpoint method. Nothing stopped me from doing the left endpoint method. Right? So I could have gone here and done the same thing, except in blue, used this point instead and found that useless area. Right? And then done this. And then done this. We'll write this sum. And so tell me about that sum. I'm still going to make, what's the length of each interval? Oh, the width, I should say. It's still 1/2, right? But instead, if I pick the left endpoint method, so this is the right, the left would be 1/2 times the first one? 0, right? So it's nothing. Because this is where the height is, so you plug in 0. So 0 squared.
1/2 square.
Right? And then it's just like you're 1 off, right? That's 1/2 times 3/2 squared plus 1/2 times 2 squared. 1, 2, 3, 4, 5 plus 1/2 times 5/2 squared. So that's the left endpoint method. Looks like from the picture that the graph is going to be, or the area is going to be an under approximation.
6.875.
6.875.
Oh, wait,
No?
no. Oh, wait, no.
I think that's right.
6.875? Okay. So the answer, it looks like it's somewhere between those two. What is it? 9. The answer is 9. Okay. Of course, question marks about that, right? All right, so here's how we're going to get the exact answer. We make a remark. And we say, well, it looks like x squared is nice and continuous. From 0 to 3, right? And so what is it that we do? We take these rectangles, and one of the things that we notice is that when we took 6 rectangles, then we got an approximation using the right-hand endpoint method. And so now I'm going to take 20. Right? And so that what's nice about continuity is that if you take more rectangles, when you do this, you'll get a better approximation. The more rectangles you take, the better. So I'm going to take as many as I can. Right? So here when I take 22 rectangles, right? And here it looks like, which endpoint method does it look like I'm using? This looks like an over approximation. It's the right endpoint method, signified by a 1 here. Okay. Then what number did they get? 9.626. Let's verify the number that you got earlier. When n is, we had 6. You got an 11 point, where is it? There it is. Excellent. Excellent. Okay. But we know what we need to do, right? That the more rectangles we take, the better life is, right? So that's an over approximation. That's better. That's better. That's better, right? Seems like the more we take in to be, the better the approximation. And this is because of the continuity of x squared. This is because of the continuity of the function. This is why we really want the function to be continuous. You can imagine that there might be some examples that if you take more and more rectangles, it wouldn't matter. You still wouldn't be able to deal with it. Right? Tons of examples, right? So we know what's going to happen, player. We want to know the exact area. When n is 4, we get 12.65. When n is 15 or 16, you get the area is 9.86. When n is 42, you get 9.32. What do we want to take n to be? What do we want to do to n?
Increase here.
That's right. To increase it to 35? To infinity. I want n to go to infinity. Sounds like a limit. That sounds like a limit. If we want to find the exact area under the curve, we're going to take the limit as n goes to infinity of that thing. Okay? So that's the plan. Go ahead.
Is that how they got one for the area of normal curve?
Oh no, that's a longer process. Yeah. So we can talk about that for sure. All right. So that's what we have to do. Okay, and that's how you get the answer. Now, as you know, that's ridiculous, right? To have to do that every single time would be a very difficult thing. We are going to do this a couple of times, get nauseous, and hopefully, bring Newton and Leibniz into the picture to rescue us. Right? So these are people who have thought about this already. Okay. All right. So we notice that as n gets larger and larger, this number approaches the number 9. Right? So of course you have to ask, well, how did you get 9 so quickly through this whole process, right? Because every time we did this, right, even for 6, this was long. How are we going to do this for 60 by hand? Right? That's the point. Okay. All right, we need notation. As you can see, it looks like we're going to be adding up a lot of things. So I want notation for adding. Okay. Yeah, that's right. So I'm going to have a sequence of things. So when I write this, so this represents the sum. And so I'll have a sequence of things. For instance, I equals 1. Do you prefer a letter? I, K?
J.
You prefer J? I don't think we really use J. I is okay. I equals 1 to 4 of I squared. When I is 1, I squared is 1. When I is 2, I squared is 4. When I is 3, I squared is 9. And when I is 4, I squared is 16. Questions about that? The sum, this symbol just means add those up. Right? So that this would be 1 plus 4 plus 9 plus 16. And hopefully you saw from the example that we did that particularly if we intend to add up infinitely many of these rectangles, then this notation would be nice because I don't want to write infinitely many plus signs. The great skeptic has come back in and said, what did you just say about adding up infinitely many rectangles? Isn't that going to give you infinity? Let me just show her the picture, and that it is true that we want to take this thing to get larger and larger. And maybe I can go in and change this. So they let me change this. Right? I don't want to break it. Right? I'm afraid now, right? But we just keep going. Look at the number at the bottom, right? It just gets closer and closer to 9, right? And so when you take n larger and larger, it's that number, right? And so in terms of the sum, we want to be able to write, if for this particular approximation, one line that represents adding up 500 things, right? So let's set up the situation in general. You're going to be given a function f. The function is going to be defined on a to b. We'll start off with a function that's continuous. I want to find the area under the curve. We're going to break a to b. Some people like the word partition. Partition. A to b into n pieces. And they're equal and equal pieces. Each piece has, what's the length of it?
B minus a divided by n.
That's right. It's b minus a over n. All right, so we did 3 minus 0 over 6.
Can't b be negative?
Yeah, and that means a is negative.
It can't be positive.
Wait, what, I'm sorry, say that again.
Oh, never mind.
Okay.
No, yeah.
Yeah, I mean, b minus a is always positive. B is bigger than a, b minus a is always positive. So we don't have to worry about the sign. That's a good question though. So in each piece, select a value for the height. We need to call that something. Let's call it, no, it changes. So so let's go back.
Oh, for the left and right.
Yeah, so in each subinterval, where is it? Yeah, in each one of these pieces, was it here? Well, we can redo it. So in each one of these pieces, we can just look at the picture. So when this is smaller, right? So I broke up 0 to 3 in the 10 pieces, in each piece I picked the place where I want the height to be. So this would be the first interval, the second interval, the third interval. So I pick an x1, an x2, an x3, an x4, and so forth, right? So in each piece, you pick a value. We can call it xi for the height. So in the first piece, it was x1, in the second piece, it was x2, and the third piece, it was x3. And the ith piece is x sub I. Right? An approximate value for the area is given by b minus a over n times f of x1 plus b minus a over n times f of x2, and then you have n of these, b minus a over n times f of xn. That's an approximate value for the area. This looks ugly. We're just going to use notation to clean this up. I'm going to call that this. So it's like delta x right? So I can call this, so this is delta x times f of x1 plus delta x times f of x2 plus, and usually we put it second. Add up n of these. And then we'll use summation notation. This is equal to the sum. Looks like I'm just adding up. I equals 1 to, where do I finish? N of f of x, not n, I times delta x. So here, let's talk about all these pieces. This is, what is this again?
B minus a over
No,
n.
yeah, but what does this represent?
Length of the interval.
So this is the length of the interval. What is this?
Height.
But yeah, but it was the function that was given, right? So this is the height, indeed. Height. What is this for?
The values, the x values for the height.
The x values where you want the height to be. Where is the height taken? Where is the height taken? And what is this symbol for?
Summation.
That means you need to add up the rectangles. Okay. Translating all the pieces of this.
Is that for like left end and right end?
That's for all the methods that we're going to use, yeah. Questions there? So yeah, so when I was doing the right-hand endpoint method for x squared on the interval a to b, right? So let's rectify all of this stuff. So for the example I did before with x squared, how did all of these things come into play? So I wanted 6 rectangles, right? Where does that 6 play a role? Here, right? Where else? There, right? The function's x squared. I chose the right-hand endpoint method. That's what xi is for, right? And then I needed to add them all up. Right? The actual area under f is defined to be the sum I equals 1 to n of f of xi times delta x. And what do I have to do with n? I want the actual number. So I have to take more and more n, to take infinitely many.
And equals to
Say it again?
the limit is n.
The limit is n goes to infinity. That's the actual area. I want to, yeah, please go ahead.
Is it okay if you use something like J instead of I as long as you keep it consistent?
Yeah. Yes, go ahead.
Can you answer this conceptual question? Like, how do we prove that for an increasing function, that using like the right limit sum is an over approximation?
Oh, that's a great question. So you're taking extra credit away from me, but that's okay. That helps my problem. So let's use our example. The claim is, why is it? What made this an over approximation? That it's increasing, right? And so if it's so now that we have the definition of what the actual area is, then what's going to be the case about this here? So if this is the actual area, then what is it that we know about when we do an approximation for any n, because it's increasing when you look at the right hand. So you mean the right hand endpoint method, right?
Yeah.
So the right hand endpoint method, what is it about picking the right hand endpoint on that subinterval? Because it's increasing.
Not starting left or you're starting left over whereas left you're starting from the origin to it.
That's right. Oh, but okay, so that's right. That's right. But this one also has to do with the subintervals, right? So if you have something that's, so this is not the proof, this is a sketch of the proof. So if you have something going up, right, and you know the actual area is whatever it is, how do you know that this is an over approximation? Because on each subinterval, what value are you picking for your height? If it's the right endpoint, what value is this on this interval? What's special about this one versus all the other values you can pick on this interval? It's the what? It's the largest, right? Because f is increasing, when you pick the right endpoint method, that's the largest value. So your approximation, this value is always larger than any other method that you pick for this increasing function. And so now I have a sequence of values that are all bigger than the actual value. And so when I take the limit, will the limit be bigger?
Yeah.
Yes. Right. So yeah, so when you take the limit of the right hand endpoint method, it's always greater than or equal to the actual answer. So that's a sketch for the proof, right? It's because for the right hand endpoint method, each approximation, this value that you pick is always bigger because f is increasing, and you can show the same thing for decreasing. All right, thank you for your question. Okay, great. So I need notation for this. This is the actual area, right? And so what does this have to do with? So I'm going to come up with notation for this. It's got to involve f of x. Now we're going to add some other notation to denote the fact that this is about x. Right? So when we move up a level in Calc 3 and so forth, that we'll have functions of more than one variable, and we'll be adding up in all sorts of ways. So I'm going to denote the fact that this is with respect to the letter x. So this means I'm adding in the x direction. This has something to do with what else? A and B, right, where you start and end, right? And what am I doing? What did I do with these rectangles? I added them, right? Or I summed them. So that's the symbol we'll use. It's the sum from A to B of f of x as a height over these rectangles. Now, I did not answer the question from the great skeptic when she came in and she said, wait, you said something about adding up infinitely many rectangles that were really, really, really small, right? And so here, we add up those rectangles here. We add up these, right? They're really, so remember, this is 3 minus 0 over 36. The length of each, the width of each one of these is 1 over 12. Right? The width of each one of these is 3 over 80. Right? And I haven't even gotten started, right? The width of each one of these is 3 over 500. That's the width of each one, and then I add up 500 of them, right? I went in to go to infinity. What's the width of each rectangle then? 3 over infinity. Nothing. And I went to add up a bunch of nothing. I get 9. Add up a bunch of nothing and get 9. Right? I add up infinitely many of nothing and I get 9. Again, this is the issue, again, about what calculus is about. Calculus is about the... That's a nice way to say it, but we have one word for that. It begins with an L. The limit. We're here because of the limit. Newton and Leibniz are geniuses because of the limit, right? That it's going to be the only thing that shows up when we define the derivative, and that when we define this, which we call the integral, the limit is here, right? And so it is our introduction to infinity that allows us to do all of this stuff, that we want to take what happens if you keep going, right? So calculus is about the limit. The limit is the most fundamental concept in calculus. Okay? The limit is the most fundamental concept in calculus. Okay? Questions about that? Okay, so whether we're taking... So again, this notion of, wow, this one thing is going away, but I'm adding up infinitely many of them. It's a fight. Right? We've seen this fight over and over again, right? Every time we take a derivative, the numerator is going to 0, the denominator is going to 0. What is that, right? This fight between infinity, something's getting huge while something else is getting small, and yet somehow it evens out to be 9, right? Go ahead.
So what is that screw lightning?
Thank you. Yeah, we need to talk about it. This?
No, not that one.
The screen. Oh, we call it the integral. This is the integral of f on the interval a to b.
Nice to just do that equation above it.
Yeah, that's what this means. Okay, so it means this. When you see this, it's the integral of f on the interval a to b. Right? And the definition is this. I'm gonna make this definition, and yeah, the definition is the limit as n tends to infinity of all of that, right? After you do all of this. Okay. The second question on the final is define this. Define this. That's the second question on the final. You might be able to guess the first question.
Fine.
Okay. No. I guess you can't guess the first question on the final. Okay. So yeah, we'll write this very clearly next time. But some of the questions, some of the things on the final will be arithmetic, and we'll do some approximation. Go ahead.
If you want delta x to be infinitely small, like how is that represented in that equation?
By this.
How does that equation know that delta x is infinitely small?
Oh, so that's the definition, right? So we're saying, so good. So as we look at this, right? Here is Here are the heights. Here's the interval we're on. Here is the infinite sum. And here are the infinitesimal widths. Is that okay? Yeah, so it's all there, right? But now it's all infinite, or it's all infinitely large or infinitely small. It's all there. Okay. Go ahead.
Can you scroll back up to where you define each piece of the...
Oh, yeah, that's kind of crucial, isn't it?
So, it's like you talk about the height.
There you go.
Thank you.
Yeah. So this is just a discrete version of that, and then all hell breaks loose when you go to infinity, right? So then this sum turns to that s, that goes to infinity, that's away, and so then this right here just becomes from a to b. You're summing from a to b. F stays. You don't really care about this point anymore. We'll talk about that in just a second when the great skeptic comes back. And then that becomes a dx to denote the fact that the widths are getting smaller and smaller and smaller. Now, the great skeptic comes in and says, well, wait, what method are you going to use to make this approximation? Now, I've been biased. I've been using the right endpoint method. So I used the right endpoint method to show that at least it looked like that as you take more and more rectangles that you should go to 9. Someone else comes and says, well, let me do the left endpoint method. You take more and more rectangles. Are you going to get the same number? Are you going to get the same number? We can look at that picture. So if I change that to the way this is programmed, 0 is the left endpoint method. If I put 0 now, let's go back and just at least make it seem like we have done something here. So that's the left endpoint method, yes? And so now when we take more values, look at the number at the bottom. It's an under approximation. And so it looks like it's approximating from below and heading up close to 9. So the left endpoint method looks like it works. It's getting close to the right endpoint method. You can pick any value you want for your choice, and they're all going to go to 9, right? And it's because f is continuous. So that this limit exists because f is continuous. Go ahead.
If you average out the left hand and the right hand, do you get 9 or no?
When
the
for any n?
When the n.
No, they don't. No, because we did. So we got 11.675 and then 6.375. I don't think they average out to be 9.
It was close to 9.
It was close to 9. Yeah, you're gonna get something close. Yeah. But you might imagine that we would not want to do 2 separate integrals and take the average.
Yeah.
It would be better to just do 1 integral. And yeah. Okay. Any questions about this? All right. We're gonna end there. I do want to talk about one thing. I get that it's Friday, right? And so we were a little bit extra chatty today. This is not acceptable, right? So we got to make sure that we are super focused 100% of the time. Okay, so it's tough. I know. It's Friday. This is why I'm ending early. I want you to have a good weekend and rest. Okay. Have a good one.
Dr. Wing?
Yes.
I asked about how they got one stick area of the normal curve.
Oh yes. That's going to take a second. Hold tight. Yes.
Why is it that first
Because it's the right endpoint method. I chose that in the first interval, and each interval I have a choice between. So the first interval is 0 to 1/2, right? I'm picking 1/2. I'm picking the right endpoint.
It was reading.
Yeah.
Thank you.
Yeah.
I didn't know about it. Hopefully it doesn't get it.
Okay, so
Yeah.
what we're going to have to do. Oh, you have a good one. What we're going to have to do is we got this function here.
Oh, this is the e to the x thing.
E to the minus x squared, right? And so you want to find the area under that thing. We got to do a ton of things. And so your question, I think it's 1 over the square root of 2 pi. So you got to do that. So to show that, we got to do all this integration stuff, and it's super hard. Okay, so you have to use some methods. So right now, I had an a and a b, right? We got to do a minus infinity to infinity. That's right. So we will not get a chance to talk about how to integrate over an infinite.
So
That's Calc 2. Yeah. Yeah.
Okay. Okay, so I got the basis of today's lesson,
Okay, great.
but I don't understand, like, how can we, what did we do when we did this?
Right, so then we went back in this interval and we chose the left endpoint method. So the left endpoint here is 0.
Yeah.
So that's why there's a 0. So it's 1/2 times 0 squared.
And then we just kept going like that. And
1/2 times, yeah,
we disregarded this.
because we only take the left hand endpoint and there are only 6. So that's 1, 2, 3, 4, 5, 6. Right? 1, 2, 3, 4, 5, 6. So there's 6 rectangles using the left endpoint. So we don't use that last one because it's not a left endpoint one.
How do we get 9 from this? Like, I know it's 9, but...
You're not supposed to get 9. They're just approximations.
So, like, when you, like, round it, you do 9.
If you take more rectangles and round it, you'll get something closer and closer to 9. Yeah.
And for this one, so this would be the distance of x, so, like, the distance of the interval.
Yeah, it's just representing the fact that the x's, the length, the width of the rectangle is getting smaller and smaller and smaller. Yeah.
And this would be, like, the height.
F is the height. That's right.
So this is the first time I've seen this.
Good, I know. This is why we're talking. Go ahead.
So this would be a to b. So in our case, this is 0 to 3.
Yeah.
So this would account for the interval. So
That's correct. That's right. Yeah, that's right. Good. These are good questions. Yeah. You have to ask those questions.
All right. Thank you.
Yeah.
Have a good weekend.
Oh, you do the same. Yeah. Okay. I'm sorry. Yeah. Okay.
So yeah, I was up to like 40.
So, at this point, this has nothing to do with derivatives. Yeah. So do you have a symbol for that for antiderivative?
No, but he was talking about, he's saying you take the anti-derivative.
Right. So right now I've said nothing about derivatives, right? But yeah, this might have something to do with the antiderivative, and I need to explain why that is. Yeah, but I'm not taking any backwards derivatives.
Yeah.
Yeah.
Thank you.
Yeah.